Okay, so we're not going to go into a deep dive into this because it gets extremely complicated. But if you're using a Geiger-Müller detector or a GM detector or a GM tube, as they're sometimes called, um, one of the things that you would use these for is to measure radioactive counts, which is a value of like how many radioactive decays are you seeing, right? But whenever you're actually using these GM tubes or these GM detectors to measure this radiation, there are a number of different things that you might not be accounting for in your measurement. Some of these are just background counts. So if we take a detector and let's just here this poorly drawn like tube here, that's the detector, okay? And if you have a detector and it's looking at nothing, the detector is just pointing down at nothing, you would think, well, I wouldn't see anything. There's nothing there. There's no radiation. But that's not true at all. You're actually still going to measure counts here. Um, uh, some of these counts are actually coming in the form of cosmic rays. You can get cosmic rays that come down, and all of a sudden, boop, your detector's picked something up. It's probably a background cosmic ray. Where do these cosmic rays come from? From the cosmos. Well, we don't know what's really producing them, but they're there, and they're totally everywhere. And you actually see most of them. If you're measuring the sky, you'll see most of them pointed straight up because that's the shortest distance through your atmosphere, versus along the horizon because that's the longest distance through your atmosphere. Which brings up another piece of information here whenever you're measuring counts. Let's say you put some material down here that was radioactive. It's radioactive, and you're trying to measure counts from it. The actual distance your detector is away, that matters because as we see in our three-dimensional geometries that we live in, as we move further away from a source, we actually start getting a spread of the different direction those particles can go. So we actually start seeing, due to an inverse square law, different transmission rates, or that this transmission falls off. We see the same thing with sound. We see the same thing with light intensity. We see the same thing with um, gravity, electric fields. Like this same idea, comes into place here due to just our three-dimensional geometries. Then you start getting other weird things that come into effect. Like, do you have air that's separating these, or is there something else in between? Because whatever you put in between here, that'll affect the number of counts you get, and you have to understand what's in between there. And then furthermore, you need to understand the geometry of the system because the geometry of the system could cause things to start bouncing in different ways, and come up and through. And you need to understand how quickly your GM tube up here is actually able to take a reading. Because what could happen is you could have a particle come up, trigger your GM tube, and then a second particle come up almost immediately, and your GM tube might not have reset in time, so you might be missing some counts. And then there's all sorts of like voltage curves that exist as you're setting these GM tubes, where if your activation voltage is at a certain region, you're just going to get like a continuous discharge on the tube, and you're just going to burn your tube out. And if you're not high enough, it's going to be very hard for you to get a reading. So there's all sorts of issues that go in with measuring radiation. It is a much more complicated thing than just taking a probe and going, we have radiation here. It's much more complicated than that. So before you actually take any sample measurement, it is important to take it without the sample there so you can get background counts. These background counts, could include cosmic rays. And then to understand the entire geometry and the setups of your system, and to really understand just what kind of detector you're using, what are the limitations of that detector, and what settings you should be using there. So there's all sorts of things that go into this. It's kind of wild and crazy, but that's why there's entire fields for nuclear engineering dedicated to these types of issues, and subsets of fields within that just into measurements. So this is not a deep dive. If you're getting your PhD in this, and you're like, well, what about this field? This is very much a surface level discussion here, but it is something to bring up in terms of measurements, because oftentimes, as we're moving through high school physics courses and intro physics courses, measurements are just bloop, and we have a measurement. We don't have to think about all the issues that come with them. But for radiation, you very much have to always be thinking about the issues that come with your measurement, and how you're taking that. Okay? So this little video here is finished, And if you've made it through every single video in the Coach Botzer YouTube channel, all of the CP intro physics videos for mechanics, and then all of the AP Physics 2 videos, and then possibly all the AP Physics C mechanics and all the AP Physics C E&M videos, you have done it. You have covered the gambit of what I have to teach you. This is the end. But it might not be the end of your learning experience. You're going to, if you're really interested in this, like continue learning, keep diving in and finding new things. As you take further and more accelerated courses and harder things and new topics, like you might become super interested in one of these and make that your career focus. And I really hope you do so. And if you end up going into some sort of science or engineering field, even if it's chemistry or biology, like please let me know. Let me know how you're doing out there. And this is the last time. Adios. Take it easy.